Let's take a look at questions 1 to 12 on worksheet number 5 that we had for homework last night. They're velocity time graphs. Okay, you know that when you see a velocity time graph, when it's titled velocity versus time, that is, you know that you should expect to see velocity on the y-axis, time on the x-axis. What would be our responding variable here? What would be our responding variable? Not the one that causes the change, but the one that is changed because of something else. Which one would it be? Yeah, it'd be velocity. We know that because it appears first in the title, and it's on the y-axis of our graph. This is a straight line. This means that it is constant acceleration or uniform acceleration. In fact, it's constant positive acceleration, right? It's speeding up. You can see clearly that, look, the speed starts at, what, 1 meter per second north, and then it goes up to 2, 3, 4, 5, 6, 7 meters per second to the north. So clearly it is accelerating. Okay, number one, we want to find the velocity of the object at 6 seconds. How do you find the velocity of an object at a certain time on a velocity time graph? Yeah? Good. You're going to go up and over. So at 6 seconds, we're going to go up and over, and it looks to be, when I do that, it looks to be 5 meters per second. So the velocity at that time, 5 meters per second. It's changing, so it's only at that moment in time, but at that time it is 5 meters per second. 2, what's the change in velocity between 0 and 9 seconds? Well, if you want to find a change in velocity, then you better find an initial velocity and a final velocity, and then just subtract the 2. At 9 seconds, 8, what do we got here? 6.4, 6.8. We're going up by 0.4s again. So this is going to be 8.4, 8.8, 9, right at the end here, right at the very end. At 9 seconds, looks to be 7, isn't it? 7 meters per second. That's our final velocity at 9 seconds. At 0 seconds, our initial velocity is 1 meter per second. So we're going to say 7 minus 1 is 6 meters per second. Now, how do you find the acceleration? There's 2 ways that you can think of this, right? Yeah, you find the slope, right? The slope is rise over run. What's the other way that you can think of it? They both end up being the exact same thing. Slope is delta y over delta x, or rise over run, and the other way is, yeah, a is equal to delta v over delta t, right? If you say a is equal to delta v over delta t, that's exactly the same thing as saying slope is equal to delta y over delta x. Delta v or delta y here would be 6 meters per second. Okay, we just found that. And delta t would be 9 minus 0, or 9 seconds. So that's going to give me an acceleration of 0.667 meters per second squared. Or it would give me a slope of 0.667 meters per second squared. But of course, that slope represents the acceleration. Calculate the displacement of the object now. The displacement of the object. This one is the one thing on a velocity time graph that's different than a position time graph. We haven't done this at all to find anything on a position time graph. Who remembers how to find the displacement on this velocity time graph? Yep, Mason? Yeah, you're going to find the area, right? Now, be careful. This one's tricky, actually. First one that we have is a little bit tricky. Okay, here's what people will want to do. They'll say, well, this is a triangle, right? Goes over to 9 seconds. Right, that's 8.4, 8.8, 9 seconds. And this goes to 7 right there. So they're going to say, well, look, the area of this it's a triangle, so it's 1/2 base times height. The base goes from 0 to 9. The height goes from 1 to 7. So we're going to say the area of this is half of 9 times 6, which is going to give me 27 meters. How many people said the answer for this is 27 meters? Not very many, because not very many people actually did it, I guess. But that's not right. I mean, it's not wrong, but we're just not finished yet. Okay, we also have to find the area of this section. Just because it's underneath, just because it starts at 1 second or 1 meters per second here, doesn't mean that we don't have to include everything between the line and the x-axis. So this was actually a little bit easier because it's a rectangle. is base times height. The base is 9 seconds. The height is 1, which gives me 9 meters. Now we're going to add those up. 27 meters plus 9 meters gives me 36 meters. How many people said 36 meters? Okay, got a few people that said 36 meters. Good. Good. Make sense? Now, I didn't ask this question, but I could have asked you one more thing. What's the average velocity? What's the average velocity? How would you find the average velocity? Yep. Yeah, you know what, let's do it a standard way, because it'll work all the time, even if it's not a nice even shape like that. The easiest way to find the average velocity, day 2, physics 20, average velocity is V is equal to delta D over delta T, right? The displacement over the time. We just found the displacement, 36 meters. We divide that by the time of 9, and we'd say we get 4 meters per second. Make sense? Now, gosh, if you take a look at that, if I understood what you were saying correctly here, say like, well, since it's a nice straight line, it would just be kind of halfway in between. Well, halfway in between 1 and 7 is 4, right? Which is exactly what we just got when we divided the displacement by the time, right? So it ends up working out, but your way only works out if it's a nice, smooth, straight line with nothing else there, right? My way, saying V is equal to the displacement over time, works no matter what. Okay, does that make sense? But in that case, you do get the same answer. Okay, next one. Also a velocity versus time graph. What's the velocity of this object at 6 seconds? So we're going to go up and over. That's going to be, we're going up by ones here. So that's going to just be 4 meters per second. 4 meters per second to the north, or we could just leave it as positive 4. The change in velocity between 0 and 8 seconds. Watch this one. The final velocity at 8 seconds is 0. The initial is 16. So the change in velocity is not 16 meters per second, but rather it's negative 16. Which should make sense, right? It's slowing down. It's decelerating. It's negative 16 meters per second. Or what else could you have said besides negative 16? What's the other way you could have expressed that and done it correct? 16 to the south, somebody said, yeah. It's positive 16 to the south would have worked just fine as well. Next one, 7. What's the acceleration of the object? The acceleration of the object and the displacement of the object. The acceleration of the object is delta V over delta T. Or you could say it's the slope, rise over run, same thing. Delta V is, well, we just found it, is negative 16 meters per second. Delta T is 8 seconds. So we've got a nice 2.0 meters per second squared. Sorry, negative 2, right? We know that shape represents negative acceleration. Sure enough, the math tells us it's a negative 2.0 meters per second squared. And finally, the displacement. Well, this one, the displacement's easier because it's just one nice little triangle here. The displacement, or the area, is equal to 1/2 base times height. And the base here is 8 seconds, and the height is 16 meters per second. How is it that when we calculate an area, we get displacement? Take a look at this. The base is seconds, the height is meters per second. Seconds cancel, and I'm left with meters. That's displacement, right? Half of 8 times 16 is 64 meters is my displacement. Josh, how are we going to find, we weren't asked this, but how could we find the average velocity here? Yeah, you can say displacement over the time. Now, in this case, we could use your method as well because it's just one straight line. So it would be, what would we get here? If we use your way, we just say 1608, right? If we use my way, we'd say the displacement, 64 meters, divided by the time, 8 seconds, and we get 8 meters per second. Same thing. Again, that only works, though, if it's one straight line. All right, there were 4 more questions. Your method wouldn't work with this one, right? Because we got a straight line. We got 2 straight lines there, right? Determine the velocity at 12 seconds, up and over. Okay, 10, 11, 12. At 12 seconds, we're going to say it's 5 meters per second. The acceleration between 0 and 8 seconds. This is the first phase. I'm going to say delta V over delta T, but you also could have said A is equal to delta V over delta T, or the slope. Yeah, same thing. Whatever way you prefer to think of it works here. The change in velocity between 0 and 8 seconds. This is 8 seconds right here. Change in velocity is 5 minus 0, and the time, of course, is 8. 5 divided by 8. I want to say that's 0.625. Is that right? 0.625 meters per second squared. What's the acceleration between 8 and 18? Oh, who's got an answer for this one lightning fast? It's acceleration between 8 and 18, Colton? 0. How'd you know that? Good. Yep. It's a uniform velocity, a uniform motion, constant velocity. It's not accelerating. Acceleration's got to be 0. Now, you could have said A is equal to delta V over delta T, but what would delta V be? 0. And 0 divided by time is 0. That's one that I wouldn't expect you necessarily to show your work. If you just recognize that that's a straight, flat, horizontal line, and that represents constant velocity, you could just write down the acceleration as 0 without showing work on that one. The displacement of the object. Okay, we've got a triangle and we've got a rectangle. We'll say area 1 is equal to 1/2 base times height. That's 1/2 of the base. It goes to 8, I think, 5, 6, 7, 8. And the height is 5. That's going to give me 20 meters. The area of the second section, which is a rectangle, goes from 8 to 15, 16, 17, 18. From 8 to 18, which is 10. And the height is 5. The displacement is going to be 20 plus 50, which is 70 meters. Here's one for you. Just a quick little aside here. What if the graph looked like this? This is velocity on the y-axis, time on the x-axis. And you had a graph that looked like this. You would find an area right here, area 1, an area right here, 2, this one, 3, and this one, 4. Does that make sense? What's the difference between area 3 and 4 and 1 and 2? Yeah? Yes, we would make them negative. Right? It's a negative velocity, which means you're going to get a negative displacement in there, right? So if this happened to be 20 above the x-axis and 50 below the x-axis, we'd say 20 plus negative 50 gives us negative 30, and our total displacement would be 30 to the south in that case. All right? I think that's it, isn't it? Yeah, it is. Now, if we wanted to find the average velocity here, we weren't asked this, but if we wanted to find the average velocity here, how do we go about doing it? Displacement over time, right? The displacement is 70 meters. The time is 18 seconds. So we'd say the average velocity is 70 meters divided by 18 seconds, which gives me, I don't know what that is. 70 divided by 18. 3.8, 3.9. Now, Josh, if we went and did it the other way, which is not a valid way for this one because it's not just one straight line, look at what we'd say. We say, well, the initial is 0, the final is 5, so the average would be 2.5, right? And clearly that's wrong, right? Now, why doesn't it work? Well, because we were going at 5 meters per second for longer. Right? It's like you're driving to Edmonton at 100 kilometers per hour for 3.5 hours, but then you stop in Red Deer for 5 minutes and you're going 0. Your average velocity isn't 50, right? Because you're going at 100 for longer. Because you're going at 5 meters per second here for longer, it's closer to 5 than it is to 0. We can't just say 2.5. Okay, the only way that works is if it was just one straight uniform line like we had in the last 2 questions. Okay, so just watch that. This way always works. That way sometimes works. Good.